Hey everyone, in this video I'd like to talk about the IEEE 754 standard. This standard outlines how to represent floating point numbers in binary. But first, what is a floating point number? Well, a floating point number has a fixed number of significant digits, but the decimal point can be placed anywhere relative to those digits. So, what does this look like in binary, and how can we encode it in a way that computers can understand? First, let's see what a binary number with a binary point looks like. Here, we have a binary number with 4 digits before the point and 4 after. You probably already know how to convert the integer part of this number. We have the ones place, twos place, fours place, and eights place. In this case, the fours place and eights place are both 1, so our number is 4 plus 8, or 12. But what about the digits after the point? Well, if each place to the left of the point is 2 raised to the x, then each place to the right of the point is 2 raised to the negative x. So first we have 2 to the negative 1, or halves place. Then the quarters place, eighths place, sixteenths, and so on. Converting each place to decimal and adding them up, we have 0.625. Putting the digits before the point and after the point together, we see that this number is equal to 12.625 in decimal. But computers can't store a point. They can only store ones and zeros. So how do we get this into a format a computer can work with? That's where the IEEE 754 standard comes in. The standard defines 5 different formats for storing floating point numbers. The most common are float and double, but we're going to focus on float. A float is 32 bits long and is divided into 3 parts: the sign bit, highlighted in blue, the 8-bit exponent in red, and the 23-bit fraction in green. You might be able to tell by the names of these components that a float works sort of like the scientific notation that we use for decimal numbers. The way these 3 components affect the number that a float represents is a little complex, so let's go over them one at a time. First is the sign bit. This is the simplest part. The sign bit indicates whether the number is positive or negative. If it's a 1, the number is negative. A 0 and the number is positive. Next is the exponent. If you remember scientific notation, this is exactly like the times 10 to the something part. In this case, since we're working with binary, we would use times 2 to the something. That something, the number in the exponent, that's what's stored in the exponent part of a float. There's something special about the exponent though. We want floats to be able to represent both very large numbers and very small ones. Very small numbers require negative exponents. So to get the actual exponent from these 8 exponent bits, we subtract what's called the bias, which is 127. This means that those 8 exponent bits can represent any integer between negative 127 and positive 128. Those 2 numbers I just mentioned, negative 127 and positive 128, those are actually reserved and they can't be used for regular numbers, but we'll talk about them in a moment. All the other numbers between those 2 are fair game. Finally, we have the fraction. This part is just like the significant figures on the left in a number written in scientific notation. There's something special about this part too. When you write a number in scientific notation, there must be only 1 digit to the left of the decimal point, and it cannot be 0. This is called normalization, and we do the same thing with binary numbers. This is where a little bit of magic happens. On the right of the equal sign in these examples, you can see the normalized binary numbers. What do they all have in common? The digit on the left of the point is always 1. The IEEE 754 standard cleverly makes use of this. The number stored in the fraction bits of a float does not contain the leading 1, because we can just assume it exists. This is called the hidden bit, and it frees up 1 extra bit to use for more precision. Here's those significant digits converted to their 23-bit fraction representations. Notice how the bits are exactly the same, but the leading 1 is missing. This brings up an important question. If we assume the fraction always starts with a 1, how do we represent 0? This is where I talk about those reserved numbers that the exponent can represent. If the exponent bits are all 0, the standard says that the hidden bit, the leading 1 in all normalized numbers, is 0 instead of 1. In other words, the number is subnormal. The actual exponent isn't negative 127, it stays at negative 126. But since our leading digit is now 0, we can now represent even smaller numbers. What does that have to do with representing 0? Well, without that hidden 1, if our fraction is all zeros, our number is 0 instead of 1. I mentioned that the exponent 128 was reserved too. So what secrets are hidden there? Well, if the exponent is all ones, i.e. equals 128, and the fraction is 0, the number is defined to be infinity. If the exponent is all ones, and the fraction is anything but 0, the float is defined as not a number, or nan for short. Nan is a useful thing to have in case someone tries to, say, divide by 0. An interesting result of this format is that, since the sign bit is separate from all of this, you can have positive and negative infinity. Strangely, you can also have positive and negative nan, or even positive and negative 0. That about covers everything I wanted to get to in this video. In the next one, I'll talk about the process of converting decimal numbers to and from binary floats by hand. See you then.